Hello students and welcome to Chemistry B. I'm Miss Slate and today we're going to be talking about kinetic molecular theory. So we're going to cover the basic principles of kinetic molecular theory, as well as Graham's law of diffusion, Dalton's law of partial pressure, and how to use dimensional analysis to convert between the many different units of pressure. So first off, the first thing about kinetic molecular theory is just that all matter consists of very tiny particles and that this matter has mass. And these are all things that we've talked about before. The next thing that is a key part of kinetic molecular theory is that all particles are in constant random motion. So particles in a solid are relatively stuck together, so they just kind of vibrate in place. Liquid particles flow around each other, but are still relatively, stuck together. There's still moderate attraction between those particles. Gas particles move in straight paths until they collide with something. And the motion of one gas particle is completely independent of the motion of the other particles. Because again, the attractions between gas particles are extremely weak. So gas particles are what we're going to be focusing on with kinetic molecular theory, and they are very small compared to the distance between the particles. So a gas consists of mostly empty space here. And this diagram is showing us a comparison of, relatively the same number of particles in a solid, a liquid, and a gas. And you can see just how much more spaced out a gas is. Gases tend to have about 1/1000th the density of the same substance as a liquid or a solid. So that's 1,000 times more empty space. So they have very low densities. Gases can also be easily compressed, again, because of that low density and all the empty space between the particles. And again, because gases are so far apart, there is essentially no attractive or repulsive forces between gas molecules. And we assume that there's just no attraction between them most of the time. The temperature of a gas is the measure of its average kinetic energy, or the motion of the particles in the substance. So not all particles in the substance will have the exact same kinetic energy. Some will be slightly faster and some will be slightly lower. The temperature is the average kinetic energy of all of those kind of added together. So on average, at a higher temperature, gas particles are moving faster, and at a lower temperature, particles are moving slower. Diffusion is when we have the movement of one substance into another. So in the cases of us, we're going to be looking at one gas moving into another. So in the diagram, you can see the gas trapped in the bottle moves out and mixes with the gas particles in the air. So diffusion is partially dependent on the mass of a particle. So a more massive particle is going to move much more slowly, and a less massive particle is going to move a lot faster. And so the lower the mass of the gas particle, the faster it's going to diffuse. And Graham's law of diffusion is a way for us to calculate the rate of expansions of gases. And that's because the rate of expansion is inversely proportional to the square root of their molecular masses. So you can take the rate of substance A divided by the rate of substance B is going to be equal to the square root of molar mass B over molar mass A. Or you can abbreviate it down a little bit smaller. Now let's look at an example problem of Graham's law. This example says ammonia and hydrogen chloride gases are released on opposite sides of the room. Will they meet in the middle of the room? And what is the rate of diffusion of NH3 to HCl? So Graham's law of diffusion, what we're looking for is we're trying to figure out the rate of ammonia to the rate of hydrogen chloride, which according to Graham's law of diffusion is going to be equal to the square root of the molar mass of hydrogen chloride divided by the molar mass of ammonia. So we just need to figure out those 2 molar masses, and we can easily solve this problem. And so we get a rate of about 1.46. As for the other question, will they meet in the middle of the room? The answer is no. So hydrogen chloride is notably more massive than ammonia. And so we know that ammonia, being less massive, is going to move faster. And so it's going to get to the middle of the room well before hydrogen chloride does. And that's Graham's law of diffusion. Now let's talk about gas pressure. So gas particles, we know, are moving around in random straight line motion, and they're colliding with each other and the walls of their container and bouncing around. It's these elastic collisions that cause pressure. So gas pressure is the result of particles colliding with their container. There are many, many different units of pressure. So the one we're probably most familiar with is the English unit pounds per square inch, PSI. But also an English unit is inches of mercury. The other units are metric units, so there are atmospheres, ATM, which is very commonly used in chemistry. Kilopascals, kPa, which is the common unit of pressure used in countries that use the metric system. Millimeters of mercury, the metric alternative to inches of mercury, and torr. And that doesn't even cover all of the units of pressure. There are many different pressure units. So one thing that's going to be important is being able to convert between them. So here are our pressure equivalencies. 1 atmosphere is equal to 101.325 kilopascals, or 760 torr, or 760 millimeters mercury, or 30.0 inches mercury, or 14.7 psi. Now, these conversion factors will be given to you on the test, so you don't necessarily have to memorize them. Now let's work through an example where we're going to do some basic unit conversions using dimensional analysis. So our first pressure example says today's weather reports states the barometric pressure is 29.75 inches mercury. What is the pressure in kilopascals? Well, just like any other dimensional analysis, we're going to start with the number they give us, 29.75 inches of mercury. And I'm going to put that over 1. I need to cancel inches of mercury, so it's going to go on the bottom. And I want kilopascals. And if we go back to our conversion rates, we can see that 101.325 kilopascals is equal to 30.0 inches mercury. So that's the conversion factor I'm going to use. 101.325, 30.0. So I do 29.75 divided by 30, and then times 101.325. And our final answer, rounding to significant figures, is 100.5 kilopascals. Let's do another pressure conversion. This one says my tire pressure is 32 psi. What is the pressure of my tire in kilopascals? Well, again, we'll set it up like we always do. 32 psi over 1. I want to cancel psi, so it's got to go on the bottom. Kilopascals go on the top. So if we go back to our conversion factors, 101.325 kilopascals is equivalent to 14.7 psi. So that's what I'm going to use. So 101.325, 14.7 psi. So then I'd do 32 divided by 14.7 multiplied by 101.325. And rounding to significant figures, we get 220 kilopascals. And so converting pressure units is very simple because it's just basic dimensional analysis, so all things that we've done already. Now let's talk about mixtures of gases. So air, we know, is a combination of many gases, as we can kind of see in this similar diagram. Now, Dalton's law of partial pressure tells us that the total pressure of a mixture of gases is equal to the sum of the pressures of each gas in the mixture. So you can think of your total pressure as being equal to the pressure of the first one, plus the pressure of the second one, plus however many gases make up the actual mixture. Now let's work through an example problem of Dalton's law of partial pressure. So this problem says a mixture of hydrogen and oxygen gas has a total pressure of 7.00 atmosphere. What is the partial pressure of oxygen if the partial pressure of hydrogen is 4.30 atmospheres? Well, remember, according to Dalton's law of partial pressures, the total pressure of the gas in this case is going to be equal to the pressure of hydrogen plus the pressure of oxygen. Well, we know that our total pressure is 7.00 atmospheres, and we know the partial pressure of hydrogen is 4.03 atmospheres. So to figure out the partial pressure of oxygen, we're just going to have to do some basic subtraction. So we get a partial pressure of oxygen gas, again rounding to significant figures, of 2.70 atmospheres. So Dalton's law of partial pressure problems are pretty simple. They either just involve adding or subtracting.